direction opposite where the flow is coming from, you're able to make measurements of head that you can use to determine, to estimate velocity at a point. Okay. Now the principle behind the operation of a pitot tube is that, of course, I think when we're looking at streamlines, we said streamlines normally we always, when there's a fluid flowing, we always have streamlines of flow parallel to the boundary of the solid body. Not so. We have streamlines parallel to the boundary of the solid body. Now, if you look at streamline that is labeled 1, 2, if you have that blunt body, that solid body, and it's put at a cross section, immersed within a flow, then the streamlines, the streamline 1 to 2, the one that is coming directly into the blunt body, there's a streamline that comes directly into the blunt body. So at point number 2, the velocity of that streamline is reduced to 0. It becomes 0. There is stagnation at that point, at point number 2. Those that have grown up in villages and that have swum in streams, you know that when you stand in a stream of flowing water, you can put a jerrycan just in the direction where the flow is coming from. You can put the jerrycan on your legs and hold it by your legs, and the water cannot move it because you are acting as a blunt body. Your legs are acting as a blunt body, and just before you there is a stagnation there. At that point, there are no velocities to sway off that object that you float at that point. So so those are the streamlines that would get if you put a blunt body or solid body into water. Okay, so we've already said the streamline in the center goes up to the tip of the blunt body and stops. So at that point, it's called a stagnation point. The velocities are 0. Now we can apply Bernoulli's equation along the streamline 1 to 2. We can apply Bernoulli's equation. So if 1 is a point just before the point of stagnation, and we apply our Bernoulli's equation, we remember Bernoulli's equation. Who can remind us? Bernoulli's equation. Who can remind us of Bernoulli's equation? Are you people there?
Oh, the pressure head plus velocity plus.
Sorry? Pressure?
The pressure head plus the velocity head plus the elevation head is a constant.
Is equal to a constant. So P1 over rho G plus V1 squared over 2G plus Z1 is equal to P2 over rho G plus V2 squared over 2G plus Z2, not so?
Yes.
So if you've written that, P1, so we have P1 over rho G plus V1 squared over 2G plus Z1 is equal to P2 over rho G plus V2 squared over 2G plus Z2. Now, notice that the streamline 1, 2, point 1 and point 2 at the same elevation. So we can cross out Z1 and Z2 since they are at the same elevation. Okay? Now we have said that at point 2, we have said that at point 2, the velocity is 0 because there is stagnation. The streamline has come into a solid body, so the velocity is 0. It causes the solid body causes stagnation at that point. So the velocities are 0. So we cross out the term with V2 squared. Okay. So we remain with P1 over rho G plus V1 squared over 2G is equal to P2 over rho G. Crossing out G, because it is common in all the denominators, crossing out G, we remain with that you're seeing on your screen, P1 over rho plus V1 squared over 2 is equal to P2 over rho. So P2 is equal to P1 plus a half V1 squared into rho. So you've seen that equation where P2 has come from. Are we together to that point?
Yes. No, we are not together.
Okay. Where have I lost you?
Like, where has that G gone?
We have cancelled it out because it is common. We have cancelled it out. The G has gone out. But you can put it back so that you cancel it out yourself. It's common in all terms, in all the denominators, so it has gone out. Is it understood now? Now, so what we are seeing is that we have pressure 2, which is equal to pressure at point 1 plus a half rho V1 squared or U1 squared. Okay, so meaning that pressure at 2 is bigger than pressure at 1. If we take it this way, if a half rho U1 squared is not 0. If it is not 0, then we know that pressure at 2 is bigger than pressure at 1, because it is equal to pressure at 1 plus the dynamic head, the dynamic pressure head. Now, the difference is, so pressure at 1 only has a static head. Pressure at 1, it has a static head, but pressure at 2 has a static head, then plus, remember, the blunt body is stopping, that stagnation is stopping a moving fluid. So it has to do work against, to stop it, it has to do work. So there is that dynamic pressure that is exerted. So that's why P2 is bigger than P1. So the pressure at point 2, which brings the fluid to rest, is called the dynamic pressure. And the dynamic pressure is bigger than the static pressure. Now, if we were to look at, so rearranging the above equation, if you have to arrange the above equation, remember in this application, the application is about measuring velocity. Okay, so if we rearrange this equation, so if we make U1 subject of the formula, we'll get, what will we get? So we'll get 2P2 minus 2P1 you try to rearrange it?
Yes.
What do you get? If you rearrange, make U1 subject of the formula.
Square root 2p square root
Square root of
2 into p 2 minus p1 over rho.
Yes, square root of 2 into p2 minus p1 over rho. So this shows you that if we are able to measure pressure at point 2 and also measure pressure at point 1, the density is known because that is density of the fluid whose velocity you want to determine. So the density is known. So we can determine the velocity v1 at that point in the fluid. Yeah, and if you're interested in, of course, getting more measurements of velocity, remember when we're talking about the profile, the velocity profile at a section, we said that from the velocity towards the edges or the boundary of towards the boundary is different from the center of the fluid. So you could choose, if you want average velocity, then you can choose to take velocity measurements at different points along a cross section, and then you get your average. But the pitot tube and piezometer setup only give you velocity at a point. Okay. So how do we measure? Are we still together?
Yes.
Yeah.
No.
Where did we lose you? Hello? Hello?
The screen before this one.
The screen before.
Yeah, it's there.
Sorry?
That point. From that
you are
point.
Still copying.
That derivation
You're
there.
still copying notes.
No, I'm not copying, but the derivation yet I'm still getting it well.
No, we started with Bernoulli's equation, P1 over rho G plus V1 squared over 2G plus Z1 is equal to P2 over rho G plus V2 squared over 2G plus Z2. But we said point 1 and 2 at the same elevation, so Z1 and Z2 go out. We said that at point 2 there is stagnation, so velocity 2, V2 is 0. So that means that on the right-hand side, okay, on the right-hand side, we remain with P2 over rho G. On the left-hand side, we remain with P1 over rho G plus V1 squared over 2G. Now, G is common in the denominator as we knock it out, and it comes to that you have on your screen, which is what we've been talking about, that if you make now U1 subject of the formula, you get V1 or U1 is equal to the square root of 2 into P2 minus P1 over rho. I hope it's clear now. Okay, so how do we measure? So how do we measure P1 and P2? If we get two piezometers.
Excuse me, sir.
Yes.
Pardon me on why P2 is greater than P1.
Why?
P2 is greater than P1, yeah.
Because at point P2, there is P2 has two components. P2 has static pressure, okay? Then it also has dynamic pressure, which is causing stagnation. You see, the fluid comes and it is stopped. It comes and stopped. Now, for it to be stopped, where it is stopped, then you expect there to be work. Some work should be done for it to be brought to rest. Some work has to be done. Not so. work has to be done. So there is that dynamic component. So there is dynamic pressure at point number 2, which is higher than the static pressure at point number 1. Okay, so so we've said that if we choose, this is how we can measure P1 and P2. Remember, we said if you measure P1 and P2 from our equation, you get velocity at a point. So if we have two piezometers, where one is normal, now when we say normal, and then the other is a pitot tube, okay? Another one is a pitot tube. So we have an arrangement like that. At point 1, we put a piezometer. A piezometer is just an open tube. So we press it where its cross section, okay, we press it perpendicular to the direction of flow. Remember, that's how we measure static head. We measure it, we measure perpendicular to the direction of flow. So at point 1, that's a piezometer. Now at point 2, and this point 2, the difference from point 1 to point 2 doesn't have to be a big distance, as long as you're coming from a moving fluid to the stagnation to the beginning of the stagnation point, it can be close. So, but if you also put at that stagnation point, if you put an L-shaped tube and you face it in the direction where the flow is coming from, so we expect that water is, or the fluid the fluid is going to rise higher in that tube, in that L tube at point 2, as compared to the one at point 1. Because remember, we said, yeah, when you're studying statics, you learned about pressure heads. So the one that has a higher pressure head rises higher in the tube compared to the one that has low pressures. So that's how the setup would be. So if I have these two tubes, okay, where at point number 1, the height rises in the tube to H1. At point number 2, it rises in the tube to point H2. Now let's substitute the pressure at point number 2. Remember, we said in fluids, pressure increases with depth. So at point number 2, the pressure that we have at that point is H2 rho G. Then the pressure we have at point 1 is H1 rho G. So if you substitute in our equation, in that equation, P2 is equal to P1 plus a half rho U1 squared, then eventually we get velocity is equal to root 2G into H2 minus H1. So we've moved from pressures, okay, and now we have come to heads, because if you go to the field, if you take two piezometers, it's very easy for you to see where the head is. You can see where, yeah, the height of the fluid in the tube. Then if you have that height, then you can estimate the velocity. So U is equal to the square root of 2G into H2 minus H1. Are we together? Question? Are we together?
Yes, excuse me.
Yes, we are.
Okay,
Excuse me.
so let's see.
Excuse me, sir.
Sorry?
Are you picking me? I would like to inquire, like, what is causing stagnation at point 2?
What is causing?
How have we achieved this stagnation?
What do you think? What do you think?
I've not thought
Sorry?
anything. I've not thought that.
I know you are an engineer. You have to think. I've told you, if you have ever swum in a river, it would have come live to you, because when you block a flowing fluid in a flowing stream of fluid, when you block it, if the water that is in the immediate of that body that you have, that solid body that you have put to block the water, has velocity 0. So if where the velocity is 0, it's stagnation, because it's not going beyond. You see, it's not going beyond that point. So if it's not going beyond, that means it is stopping there, and the velocity is 0. And what happens is, if the first fluid blocks, that means behind there is some column of stagnant fluid that is created. Now, this is something that you can try out physically next time you go to when you find a flowing fluid. When you find a flowing fluid, you try it out. You try it out physically and see. Yeah, it is the stagnation, because you have blocked the flow. Okay. Good. So now this is a simplified schematic. This is a schematic representation of our pitot tube. The picture that I showed you. This one that I showed you, the one on your right. Okay. I've told you that where the cursor is, there is an opening. Then this vernier is for measuring height. And the manometer can be connected at the opening here, up here, where the cursor is, and also down here. You'll see it when you come to the lab after COVID. Okay. So a pitot tube basically combines two tubes. A pitot tube combines the two tubes. It combines a manometer, this manometer that I showed you. This is a manometer. The one on the left is a manometer. So you can connect tubes on a manometer onto the pitot tube. So it combines both a tube that measures static head and then the L tube that measures dynamic pressure head. So assuming, now let's look at that picture. If you look at point number 2, we are calling point number 2 is there because that is the entrance of an L-shaped tube. We are calling it number 2 because that's the entrance of the L-shaped tube. It's the entrance of the L-shaped. Okay, so it is the one that has a higher pressure. Now at point number 1, you have, that's where you measure at the point, that's where you measure the static head at point number 1, because you see it is lying parallel to the direction of flow. So the influence is on recapturing static head. Since the openings are parallel to the direction of flow, so we're only capturing static head. Okay. So if you were to look at the setup, and of course the manometer now with that one, you know it. If you look at that setup, let's look at the movement of the manometric fluid after connecting this pitot tube, after inserting it in a moving fluid. Do we expect the H? Do we expect that the manometric fluid is going to rise up at point A, or it would rise up at point B? Looking at the setup and from what we have discussed about static pressure and dynamic pressure. Is this assumption correct? The sketch.
To rise at A.
Sorry?
To rise at A.
It will rise at A. Why? Sorry? Why will it rise at A?
But will be pushed down and force them up.
At tube B.
I'm not hearing. Sorry? One at a time?
As the fluid goes through, the pressure will be pushed, and at the beginning the fluid will be pushed down, which will force the stage and push the fluid up.
You're saying at point B? Hello? Okay, yeah, we expect that at point, the limb that is connected to point number 2, to the opening that comes from point number 2, is experiencing the dynamic pressure. So we expect that there will be more pressure at B than A. So we expect it to rise at A. So you have to be mindful of that when you're working out problems that concern pitot tubes, because depending on how you sketch, then your answers might give you negatives, which is okay. You can get negative as long as you know how to interpret it. Okay, but this is how you should sketch it. Okay, so we already talked about that. So let's consider of course, the assumption that we use in pitot tubes is that the tube is very small, such that the diameter between point, such that you see, if you look at that, so we are considering that diameter, the diameter of this L of that tube, we are considering that the diameter is too small, such that point 1 and point 2 can be considered to be at the same level. Remember we are looking at a streamline with 2 points on the same streamline. So that's why we have to make an assumption that the diameter is small. Otherwise, the elevation of 1 and 2 are different if we consider the diameter. Okay, but that's an assumption. It's a simplifying assumption. We consider the diameter to be too small, such that 1 and 2 are considered to be at the same level. So, so if you consider the pressures on the level of the center line of the pitot tube, that is at the center line, this center line, you see this point to this center line. If we take the center line, which is marked by a height x from point B. So we are putting a manometer. What we want from a manometer is just a head difference. Remember we said U is equal to √2G into H2 minus H1. So if I know the head difference, if I know H2 minus H1, that means I can get velocity. So we are trying to to use now the theory of manometers, you attach a manometer. So that's how it comes. That's how it comes out. Let's see. So let's see. Let's look at point A. Let's look at point A. If you look at point A, what is the pressure at point A from manometers? What is the head? What is pressure at point A? If you look at this manometer, this point A, this limb is connecting to point 1, not so. It's connecting to point 1. So we can say that pressure at A is equal to pressure at 1 is equal to pressure at 1 plus what? Tell me the columns of fluids that the columns of fluid that are exerting pressure at point number A.
H rho manometric.
Sorry?
H rho manometric.
H, yes,
Rho
H,
manometric.
which is the depth of the manometric, H rho man, G,
G.
plus what else? Sorry?
The height difference
What
of
else?
X minus H pressure.
Yes, you see at
G.
point 2, you see at point 2, at point 2, if you take that center line at point 2, where it crosses above point A, inside point 2, that is still the same fluid. Even inside point 1, we still have the same fluid up to this point. And we know within the same fluid, pressure at the same level, pressures at the same level are the same, not so? In a fluid, we have these are the same pressures because they are the same level and it's a continuous fluid. So the other column of pressure that is exerted at point A is X minus H.
Rho.
Rho. Now rho for what? This rho is for which fluid?
The one above.
The flowing fluid.
Yes, the fluid whose velocity we are determining, because the one that fills up this tube up to the separation with the manometric fluid. Okay. Then what about pressure at point B? Pressure at point B. Pressure at point B
is equal to rho GX.
is equal to what? Rho
GX.
Rho GX. Is that all?
Then no, plus P2.
Sorry?
Plus P2.
Yes, plus P2. Yes, plus P2 because the pressure 2, P2 is the point, is the one that is connected to that limb. Plus P2. So that's what we have. But we know pressure at A and pressure at B are the same. So if you equate these two, it eventually comes to that, which you should be able to write out, to work out in your free time. Okay, just now collecting like terms and then looking for the value of U1. Okay. Of course, the reason in this U1, we are removing the whole of this derivation, remember we know that P2 is equal to P1 plus a half U1 squared, but we don't know what P2 is, okay? We don't know what P2 is, so we are trying to find a derivation of U1, okay, made up of items that we can easily measure. For example, if you connect and put a manometer, you're able to measure H. Now, raw manometric, the density of manometric fluid and the density of this normal of the fluid whose velocity you're determining, those ones are known. So you only measure H and then you determine your U1. Are we together?
Yes, we are.
Good. Now, notice that pitot tubes, we already talked about this. Pitot tubes only give velocities at points in the flow. It does not give the overall discharge of the stream. So it gives you a velocity. If you want to determine now the discharge of a stream, either you're going to, if you want it more correct, you can take different measurements of velocities across the section and look for the average. Okay. Yeah, but now one of the disadvantages why you cannot say use it in streams, the holes are small, they can easily block because of debris. So normally in streams, you find they prefer using current meters and other measurement devices or measuring techniques. Okay, copy that example, but you can just take a picture.
Excuse me, sir. Excuse me,
Yes.
sir. You
Yes,
said
I'm
that they
listening.
can break due to debris. You are saying that the tubes could break due to debris. Yeah, debris mean the surges in pressures. What is it?
Debris. These are okay. You call it silt.
Yeah.
Okay, they can block because of silt and other dirty particles in the water.
Okay. I get it.
Yeah, because the holes are small. Okay, so let's try to anyway copy that example and you'll try to work it out. Or we can try to work it out. Work it out and give me the answer. And let me see the time. But you can take a picture, not so. You can take a picture.
Are we going to get the lecture slides?
Sorry?
We're going to get the lecture slides.
I'm not getting you.
We're going to get the lecture slides instead of taking pictures so that we have pieces.
Take a picture of the example. Screen, you just capture the screen.
What he's asking is, are you going to give us his notes, like the slides later on for us to read?
I repeat what I told you in the first lectures, that the notes, there are lots of resources online, so you can get your own notes. Mine is to help you appreciate the principles. Okay. So what's the answer?
Screaming in my bed, in my bed. Screaming in my bed, my bed.
Matovu Abu.
I hope that one is not part of the class. That's the reason. That's the reason why I shouldn't even give you notes. Okay. So that you become more serious. Okay, who has given me the who has given me the answer? Who can give me the answer? Now, for such questions, I don't encourage you to cram the formulas because in case you get it wrong, then you're in trouble. Yet it's very easy for you to derive it there and then as you're working out. You work it out from first principles.
So I'm getting 1.61.
Sorry, volume. What's the volume flow rate?
I'm getting 1.61.
1 point. What units?
Meters cubed per second.
What units? What units?
Meters cubed per second.
Sorry?
Meters cubed per second.
What's the different answer? What's the different answer? Who's Sharif? What's the different answer? Okay, I can see two people have gotten. Okay, we are going to proceed.
Whoa.
Sorry? Oh. It's raining this side, I hope.
Lot of noise.
Hello?
I can hear
I
you.
can't hear a thing now.
I can hear you.
So we proceed, we can hear you.
We can hear you.
Oh, you can hear me? Okay. Okay, I'll try to shout. Okay. Let's proceed. Or who has got it wrong? Who thinks they have got it wrong? Who has an answer different from what has been posted in the chat? Okay, so let's proceed. Let's look at ventrimeters. Hello? Hello?
You can hear this.
Okay, okay, we're hearing you.
Yes, Pastor, you did it.
Sorry? Sorry? Hello? Hello?
I can hear you.
Hello?
So we can hear you.
You see, now the one who said he wants to see how I've done it, even if I don't calculate anything, I just substitute in 2GH. H I know I think it was given. If I look at this question, H was given. If the height measured for the attached manometer is 10 millimeters, but I will put it to meters, so that is 0.10 meters, 0.001. You divide by 1,000, you get it in meters. So I put my H. Density of manometric fluid is water. The manometric fluid in this case is water. It's the one that has the density of about 1,000 kilograms per cubic meter. Okay. Then rho is 1.2. That is the density of the air whose velocity you're measuring. Now we substitute here and substitute G, you get U1. Now the U1 gives you the velocity at the point, but we want volume flow rate because the velocity is in meters per second. Now if you want to get the volume flow rate, that means you multiply by the cross-sectional area, and the area is given. So the cross-sectional area can be determined from pi over 4 d squared. Okay, because we are talking about a duct of 400 millimeters, so that is about 0.4 meters. So we have pi over 4 times 0.4 squared to get the area, which you multiply by the velocity you have gotten to get the volume flow rate in cubic meters. Cubic meters per second. But I encourage you, don't just substitute, work it out from first principles if you meet it in the exam. Otherwise, you can get it wrong. Like here, where we have rho man minus rho, you might have it the other way. Or the question could be such that we can we can try to make it a little bit not so direct for you to pick out and substitute. So it's better to work from first principles. So that if you fail to get the answer, at least you can get for the method. Okay. So let's look at ventimeters. Now ventimeters look like that. That's how the ventimeters look like. That's the picture of a ventimeter. So we have a pipe connection to the left and a pipe connection to the right. So at the left-hand side, water comes in. Okay, water comes in, and then the cross-section area of the flow, is reduced. It's reduced so that you cause a pressure drop. It's reduced so that you create a pressure change. And then you have a diffuser there on the right-hand side. Again, the water flow gently goes back the original flow diameter. So the diameter of the cross-section on the left-hand side is the same as the diameter at the end at the cross-section on the right-hand side. So that's a ventimeter for you. So a ventimeter is also a device for measuring discharge. Now, when we talk about discharge, we are talking about volume flow rate, because discharge is a flow per time, not the speed of the flow. So we are talking about the discharge. That is for the entire cross section. So, like you've seen, it consists of a converging section. Now, the decrease in the section increases velocity, because you know, if we have Q is equal to VA, Q is equal to VA, you have the same discharge that is flowing through the cross section. Now, if the cross section area reduces, since it is still the same Q, then the velocity has to increase. Velocity has to increase. So because of the cross-section area, because of the velocity increasing, or the cross-section area reducing, there is a pressure reduction. Okay, then you have a diffuser, like you said, that takes back the water to the original dimension. So if we are to measure the pressure difference at the start of the ventimeter, and then at the point, at the diffuser, at the start of the diffuser, that is at that point of the smallest area cross section, at the smallest cross section in the ventimeter, if you measure the pressure difference, then you can use that pressure difference to determine the discharge. Let's look at it this way. How do you measure the pressure difference? Still, the pressure difference can be measured using a manometer. You can connect a manometer at point A. Okay. That is before you start reducing the cross-section of flow. And you can also, so you connect the manometer at point A, at point 1, and also at point 2. So what happens is, so the reason we have the manometric fluid rising in the limb on the right-hand side is because we've said that there is a pressure drop. So pressure at 2 is less than pressure at 1. But even if you sketch it the other way and you work it out from first principles, you will still get to the same conclusion. Okay. So if you're seeing my cursor, from this point up to this point, I think there is a way I can, what is this? Ball point, okay. So from this, it doesn't show. Okay, from this point up to this point, that is our ventimeter. Okay, that is our ventimeter. Are we still together?
Excuse me, sir, I'm kind of lost.
Where?
So you are saying that when the cross-section area reduces, that pressure reduces. I'm wondering the other pressure going to reduce when the cross-section area is reduced.
Sorry?
It does. The previous slide you were showing us, the previous slide before this. Let us go to the previous slide.
The previous slide.
Yeah.
Yes.
What we are saying, it consists of a rapidly converging section which increases the velocity of the flow and hence reduces the pressure.
Okay,
but
let's write
that
it. You're saying that?
I'm saying that when the velocity is increasing, pressure also should increase.
There you are opposing Bernoulli's principle. You're opposing Bernoulli's principle. You state Bernoulli's equation again. P1 over rho g plus V1 squared over 2g plus Z1 is equal to P2 over rho g plus V2 squared over 2g plus Z2. So if we consider that the elevation is at the same, this elevation is the same, okay? Now, if, and you know, it is equal to a constant, if in the second term velocity increases, if we are to continue, if we are to stay with the same constant, that means pressure should drop to compensate for the increasing velocity. That is from Bernoulli's equation, Bernoulli's principle. Is it clear now?
It's fine.
It's fine.
Yeah.
Yeah, so when the velocity increases, when the cross-section area reduces, the velocity increases. And when the velocity increases, there is a pressure drop. Okay? So, now, if you can still refer to this chart, refer to this sketch. Now, if we apply Bernoulli's equation from point 1 to point 2, now point 1, you see, I've told you that this is part of the pipe. Okay, it is carrying the fluid, and you want to determine the discharge. So you decided to put a ventimeter, which is from this point up to this point. Okay. So point one is just at the start of the ventimeter. So it is just inside the pipe. And then point 2 is at that small cross section in the ventimeter. So if we apply Bernoulli's equation, so we state it like that: P1 over rho g plus V1 squared over 2g plus Z1 is equal to that, is equal to a constant. So it's got P2 over rho g plus U2 squared over 2g plus Z2. But we also know that from the continuity equation, Q is equal to U1 A1, but is also equal to U2 A2, meaning that the discharge that we have at point 1 at the cross-section area 1 is the same discharge that we have going out at cross-section area 2. It's the same discharge. but the velocities are different. And the reason the velocities are different is because the cross-section areas are different. Velocities are different, but the discharge remains the same from the continuity equation. Okay, so U2 is equal to U1A1 over A2. So if we substitute and rearrange, so we are substituting for U2. Okay, the reason you're substituting for U2 is that you're not interested in the velocity at point 2. Okay, that's why we are substituting for it. We are not interested in the velocity at point 2. We are interested in the velocity at point 1 because it is the velocity that is at a cross section of the pipe, okay, or the duct, whose carrying a fluid whose velocity or discharge, we want to determine. So we are substituting to remove U2 so that we don't get another problem of trying to compute for U2, or trying to look for U2. Yet it's not our primary objective. So when you substitute for U2, it comes to that. So we have U1 is equal to A2 into the square root of 2G into P1 minus P2 over rho G plus Z1 minus Z2 all over A1 squared minus A2 squared. So in theory, that is the discharge that we would get. That's the discharge that we get. Sorry, that is the velocity. That is the velocity at point 1 that we would get. And for us to be able, so let's see. No, it's the discharge. They've already calculated. Let's see. 2. 2 squared. Okay, try to derive. U1 squared 2. Okay. I hope you have paper you're working out. You're following. You need to have some paper. Are we together? No. So U1 is the velocity at section 1, but we know Q is equal to AV. So Q Q, which we would call theoretical Q, is equal to U1 A1. But we have already computed A1. We know it. So you can substitute it. But then the Q actual is equal to a constant, which is referred to as the coefficient of discharge. Depending on each ventimeter has its own coefficient of discharge. So depending on the ventimeter you're using, it has a coefficient of discharge. So which is CD times A1, then U1. But U1 we already have it. U1 we already have it as A2 square root of those terms. So that would be the actual discharge as measured by a ventimeter. Hello?
Hello. Yes, sir. That coefficient of discharge, how is it determined? Is it determined experimental or it is just estimated?
You don't estimate it. You see, if you look at the ventimeter, hello? Hello?
Yeah, hello? Hello?
Yes, if you look, yes, you see, if you look at this diffuser, if you look at the diffuser, like this partial, they are estimating this is 6%, and then the first part is estimated 20%. Now you can have another diffuser where the first part is maybe 15% or 10% or whatever percentage. Then the diffuser is maybe 8%. Now the coefficient of discharge, is, for example, if I have, remember we are taking flow from section area 1. Now that one who is in the market should be mute. There's somebody making noise in the background. Seems somebody from the market.
I'm hearing you, sir.
So I'm saying, if you have a flow coming in at point 1, it enters your ventimeter, and then it comes out at the end of the diffuser. Now, if you have, by what point? Okay, let's see. If we are able to measure, okay, can we say that the conditions that we have at 1 can be reproduced at the end of the diffuser? Can the conditions be reproduced? As in you cause a constriction, okay, then after point number 2, the flow goes out. Okay, the flow, sorry, the cross-section area again is increased to the original size of the pipe. Can we say that the condition that we have at 1 will automatically be reproduced after the ventimeter will be reproduced at the exit point?
No.
Okay, it might, yeah, it might, yeah, it won't, but it can be close. So depending on the angles of the diffuser, the angle that you have, depending on the shape of your ventimeter, then you're going to have a different coefficient of discharge. Okay, a different coefficient of discharge. So that is that CD is taking care of the error term. Now the manufacturer can already tell you because, and it can even be determined experimentally. Okay, but each ventimeter, the coefficient of discharge would be known depending on its geometry. Okay, so you don't just assume.
Yes.
You don't assume. It is known. It's given.
Yeah.
By the
I
way, when you
get.
started, okay. Yeah, and we have a diffuser. We gently take it back. You gently take it back to the original cross-section area, so that you avoid the more friction loss and also pressure losses. There are some pressure losses that as you study in pipe flow, when you change cross sections, when the changeover is not smooth, then you create eddies, some eddy currents, which lead to pressure losses. Okay. So basically,
okay.
Basically, that's about it. That's how we can get the actual discharge. We get the theoretical discharge that we have computed, and then apply a coefficient of discharge. Okay. Then you can as well, you see, okay, this is a derivation that we got, which has pressure 1, pressure 2, Z1, Z2. Z1, Z2 can already be determined if you know the orientation, the orientation of your pipe or the duct. A1 and A2 are known because A1 is the cross-section area of the pipe where the ventilator is connected. Then A2 is the cross-section area at the throat, at that smallest diameter of the ventilator at the throat. That is the A2. Now P1 and P2 can be measured. But you see, P1 minus P2 represents a pressure difference. P1 minus P2 is the pressure difference. So which pressure difference can be determined using a manometer? Because when you connect a manometer at point 1 and another limb at point 2, we have a manometric fluid rising up to a height that is proportional to the difference in pressure between the 2 points. The way we have it there. Okay, so if we are to express what we have in terms of pressure difference, sorry, in terms of the manometric, in terms of densities, so that we only measure H and the rho man and rho are known. A1 and A2 are known, can be easily determined. CD is given. So P1, this P1. If you go back to that sketch, if I take, sorry, let me see, ball point. So if I take pressures at this datum, if I take pressures at that datum, and my left limb is A, at my right limb we have B, pressure at A is equal to, is given by pressure at A, if this is, let's see, a pen, if this is A and this is B, pressure at A is given by
pressure at 1 plus
pressure at 1
Plus Z1 rho G.
Plus Z1 rho G. Because that is because this is an open tube connected to point A. So the head of a fluid above point A is the head that is coming from this fluid, whose discharge, which is flowing in the pipe. So it is pressure at A is equal to Z1, sorry, is equal to pressure at 1 plus Z1 rho G. Now pressure at B is given by
Pressure at 2
pressure at B is given pressure at 2
plus rho GH
plus
rho GH
Rho Monometric H. Rho MN
yes
GH.
H yes. Yeah, so this goes with the manometric fluid because this is the depth. This depth is for a manometric fluid. So it's H rho man G. Then plus
rho
GH. Then plus
minus H.
Rho G
plus
Z2
Z2
minus
minus
H.
H.
Plus Z1 minus H.
Yes. Yeah,
Then
that's it.
rho G.
Z2 minus H rho G.
G.
Where rho is the density of the fluid, because the one that has flown through point 2. So that's what we have here. But we know that at pressures at point A and point B are the same. So that's what we have. P1 plus that is equal to P2 plus rho man GH plus rho G Z2 minus H. So when you correct like terms, P1 minus P2 over rho G plus Z1 minus Z2. So this term here, when you correct like terms, that term there is equal to H into rho man over rho minus 1. If you correct like terms, it comes to that. Okay?
Okay.
Okay. So when you correct like terms, so when you substitute into this, yes, if you substitute into this, so you're bringing this rho man rho minus 1 H here, and Q actual becomes that. Okay? Any question? Hello? Hello? Am I on?
Yes, we can hear you.
Any question?
No.
Okay. So in conclusion, so when you use a manometer, the ventimeter can be used without knowing its angle. Now, of course, its angle in a way dictates what the CD is, what the coefficient of discharge is. But you don't need to know the angle if you use a manometer, because you see in this calculation, you only need the height difference in the limbs, the density of the manometric fluid, the density of the fluid whose discharge you're determining, and the cross-section areas. The rest of the geometry, not necessary. Good. So So if there's no question, if there's no question, you'll do that in your free time and see if you can get that answer, 0.816. And I think you have this, in the assignment that I gave, you have a number on event limiter, which you should do now. You don't wait for the deadline. You first try out this example. When you get it, then you work out that number in the assignment. And you make sure you work it out on your own. Although you can ask your colleagues, but don't Xerox. Don't just copy. That is not learning. Okay. Are there questions in? Hello? Hello?
We can hear you.
Any question? Because we are about to be timed out in the next 8 minutes. So if there is no question, we are stopping here for today. Am I still sharing? Am I still sharing?
Yes.
Has anyone worked it out? Can we sign out? If there is no question, we meet at 9 on Thursday. Bye-bye.
No, you guys first. We're asking.
Hey, you're asking? Hello?
Yeah, we're asking. We have our colleagues that are in villages that cannot connect to these lectures. So if you're telling us that you're not going to send us these slides, how are we supposed to help them out? Should they just register the course?
How will you reach them?
Like
how will
how
you
are they
reach them?
Yes.
Like how will you reach them? I'm asking.
No, we shall get with
for you. How are you going to reach them?
If they come back to campus, we shall send them the emails. They go to cafes and get them. But like the slides, that's what we asked.
But now, if they are not attending, how will they sit exams?
No, if you send us these slides, we shall send them.
They are still organizing transport.
Their network is weak. They don't have good phones that can connect to these apps, so they are facing problems. So are they supposed to face the consequences of you not sending the notes, or we tell them to be registered at course village?
I don't know. Now, if they don't have access to internet, what do I do?
We were suggesting that you send us those slides that you're using to teach us. Maybe we shall discuss for them when they come back to campus.